Hey everybody, this should just be a short little video today. I just want to talk about these two quantifiers. So their existence for all, they show up all the time in proofs classes and they're kind of weird. So really the weird part is when you start to negate them. And I just want to make sure that you kind of understand what the negative of these two things would basically be. I used to sometimes get confused with how to negate something if I want to do like a proof by contradiction or a proof by contrapositive. So making sure knowing how to negate these is really important. So if you don't know, I feel like I've used them in both of your classes before, but these are the symbols for there exists and for all. There exists is like a backwards E, and for all is like an upside down capital A, and I have no idea why. To be totally honest, I just know that's them. So like if I took this statement here and translate it into symbols, it would read for all x in the reals, whoops, I was about to do z, the reals, there exists some y in the reals such that y cubed equals x. And that makes sense if you think about it. The one y here, so there exists means there's like this one fixed y. That would be the cube root of x, right? You could basically, I guess, I almost think of it as just substitution. Take this and put it in here, right? And you're going to get x. So this is the y value that you want to put in here to make this statement true. Orders of quantifiers is really important. If I just to show you like how different the statement is, if I just switch the quantifiers here, this all of a sudden really doesn't make sense. So now it's saying, so there is some x, so x is fixed, right? Such that for all the y's in R, y cubed is x. So that means, right, I can cube all the real numbers, right? All these. So I can cube all these real numbers and I get one fixed x. So 2 cubed equals negative 3 cubed, blah, 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 blah. All these equal x. That doesn't make sense. So the way that you set up your quantifiers is really important. Sometimes just switching two symbols in a math statement are a big difference. And a lot of harder math classes, you're actually just working with crazy things that look like this, and there's quantifiers all over, and it's really important to know how those quantifiers act and what they're actually saying. Negations of them. So this is kind of just one of those things. I think if you think about what it's saying, you could start to kind of make sense of it. But if we want to negate for all x in the naturals, like p of x or something happens, it really means we just need to find a thing that makes p of x false, right? So that means that this thing really should be equal to there exists an x in the naturals such that p of x doesn't happen, or negative p of x, right? So if you want to just think about, in order to negate this thing that has to work for all these numbers, it's basically sufficient to just get a thing where it falls apart. It's basically a counterexample is how I think of it. If we want to negate this for all, we just need to find a thing that breaks it down, right? And likewise, you kind of have the negation of a there exists being a for all. So if you want to negate there exists x and x such that p of x or something happens, it's some statement or something, you need to show that all the x's and x, not p of x happens. That's the idea. So it's sort of a flip. So it's almost like a formula, and I think it's on somewhere around page 60, I think. Don't hold me to that. But somewhere in that chapter 2, there is a part on negations of quantifiers, and there's this kind of formula almost and this formula are there. But they are important. So knowing that, like, how to do this will help you, because there's going to be a lot of times where you need to negate something to do like a proof by contradiction. And if you're negating a for all, it would turn into like a there exists. So I just want to kind of do 2 examples here. Actually, I think 3 examples, but just kind of showing how like negating of this kind of stuff can work. So if you have the statement, the square of every real number is non-negative, so we could put that into symbols as for all these x in the reals, right? X squared is greater than or equal to 0. That's just really what R says, right? It says for every real number, so for all these things, right? That's that part. You know that the square is non-negative or greater than or equal to 0. So if you were going to like do negative of R, right, you would get a there exists x in R such that not this x squared greater than or equal to 0 happens. Or just say there exists x in R where you have x squared less than 0. And, this statement is true, right? The square of every real number is non-negative, right? And you can see that this is the negation and this is false, right? We know that, like, it is not true that you can find some real number and then square it and have it be a negative. You could say there exists x in C where x squared is less than 0. That's fine. That's the definition of most of imaginary numbers, is that they square to negatives. But you can't say that for real numbers. So we definitely negated it because now the statement is false. Another thing just kind of see is there's a whole bunch of math. There's actually an area of math called mathematical logic, and what we really do in that is take these crazy symbolic statements. Like, they can get way messier than this. I only took 1 class in mathematical logic, and it was actually like a dual philosophy math class. So it was a lot of philosophy too. But we basically just almost like crank out equations with these crazy symbols. And it's good to kind of just, we won't really do this year. I just wanted you to see one. So if you can almost make these like equivalences. So you take that statement if you want to negate it, right? So that's what we're doing, negative of this whole thing in parentheses here. So we would have the for all flipping to a there exists x in R. And then we're going to have to negate all of this stuff, right? And then, now we've got another quantifier in there. So I'm going to copy this first part down. And then we've got to negate a there exists statement. So this part is going to morph into a for all y in R not y cubed equals x, right? And you could even go a little further because you could switch that out, right? So you could say, okay, there exists x in R such that for all y in R, you have y cubed not equal to x. And these can get even more complicated. The last thing I want to show you is how we kind of handle implications. So these were just purely switching around there exists and for alls. But there's a lot of stuff out there where you have like you're negating a conditional statement. And then it's even another weird thing because you're going to get a conjunction. But this is, if you like this stuff, you should look into like mathematical logic, because there's a whole branch of math where you just sort of crank through these symbols and do like little equations kind of like this. And it is actually kind of fun. I think they feel like little puzzles almost. But the last thing I want to talk about is just negations of conditional. So we talked about it before, like if P implies Q is false, that's like the lie case where P was true and Q is not. Like, I promise you will get an A in the class if you do your homework. It's like you did your homework, that's true, so you should get an A, but you didn't. And so this conditional statement is not true, the full statement, right? So that's the lie part. And we know that, the only way to get that false conditional is with the and Q not true. And so when you negate a conditional, you actually are going to get a conjunction. You're going to get, it's right there in the word and. You're going to get P true and not Q, basically. So if we just do it with this one really quick. So first I'm going to just turn this into symbols. So R would look like this X is odd. So this is like a integer. There's no like rational odd numbers or something. So for all X and Z, basically we have if X is odd, then X squared is odd. So we'll just say, I'm going to just do it this way. X odd implies X squared odd. So if I want to negate this, I'm going to switch my for all to a there exists, X in Z. And then this part needs to convert to, maybe even I'll take it another step at a time here. So if I negate that conditional, I'm going to get, let's see, so I'm going to get negative, I'm going to get P is true, so X is still odd, but the conditional will flip to a conjunction, and then Q is not true, so we're going to say like X squared is even, right? And that's basically it. If you read it off, you would see that this statement is false, which is what I kind of just paused to do. So there exists some number in the integers where X is odd and X squared is even. That's definitely not true, right? This is a negation of this original statement. And that's always like, if you're ever doing negations, you should always take time to make sure that whatever you're negating really does sound like the opposite of the original statement. And again, the reason we do this is just like, if we're going to be doing something like a proof by contrapositive, we're going to need to do negations. And so you need to know if there's like a there exists or a for all in the conditional that you're trying to prove, that you need to know how to negate it, basically.